Electronic technology has evolved during the last, especially during the last few decades, in the last 50 years around, and started using discrete components, and then it advanced to using integrated circuits where many components, mostly transistors, could be put inside a single device. And we will see how has been this evolution, and also the some types of integrated circuits. So these are some electronic devices, mostly our discrete old-fashioned electronic devices like traditional resistors, capacitors, bigger electrolytic capacitor here. This is a potentiometer, diodes here, light emitting diodes or LEDs around here, and these are discrete transistors, okay, small signal transistors and power transistors. So typically those components have these long terminals that are designed to be connected together in printed circuit boards, like this one, which is a board from a mini computer from the 80s, the famous Commodore 64, where we find these devices going through the holes of the printed circuit board. That's why these devices are called through-hole devices. And also here we have some integrated circuits of the first type. These integrated circuits typically had only a few transistors inside, maybe up to 100 transistors or some more in this case, and this is the typical way to put everything together. You have some integrated circuits with whole design in the inside, connected together with discrete devices around. The evolution of electronics has made that more and more functionality is done inside the integrated circuits, and also discrete components has been reduced the size. So a more modern printed circuit board from the beginning of the 21st century is this one, where we also have some integrated circuits. Now these circuits are connected to the board in using a technique that is called SMD, that stands for from surface mounted devices. They are soldered using these very small pins on the surface, and discrete components like this one are also soldered on top of the device. The connections don't go through the holes. Okay, these small SMD devices you find here, these come in these tiny strips. We have resistors, these are maybe capacitors, and so on. So that's how electronics behave from the outside. Now from the inside, integrated circuits, what they do is that they contain whole circuits, some very complex circuits. The difference between an integrated circuit and a circuit that you build on top of a board is that in integrated circuits we do not connect individual devices, but we fabricate all the devices. Mostly we use transistors at the same time, using different layers of material. So in here we can see that there's a bottom layer that works as a substrate, and then we grow the different layers of material that are used to build the different devices. So at some point we grow a layer of material isolating all these devices, then some masks are applied, some protective material here, and using different chemical and physical processes we create the layers of material needed to build the transistors. But we do it all at the same time. We do all these layers at the same time. we build that bottom part of all the transistors, then we put the next layer, we build the next part of all the transistors, and so on and so forth. In this example here, these are field effect transistors. Probably this is a PMOS, this is an NMOS, and they are connected together using layers of conducting material, some kind of metal. Okay, all devices are in this area here. From here to the top, we have more and more layers of interconnection, layers where we put metal around. This is a cut, so metal goes this side and also goes to the inside of the photograph. So with these layers, we are able to connect different terminals of the devices using different layers. At the top layer, we have these accesses here to put the bumps of lead of soldering that make it possible to connect from the outside. So this is a photograph of the top part of an integrated circuit where we can see the different layers of material, more or less, how it's constructed. In the end, the whole integrated circuit is a small die that is put into a package with tiny connections that go to the pins of the device that we see from the outside. Okay, but inside we can have a very complex circuit. Actually, when we build an integrated circuit, sometimes we build some specific system, like a microprocessor. This is a Pentium microprocessor, one of the early Pentium microprocessors. It includes several transistors, so a few million transistors, I think, and we can distinguish different parts of the processor. Maybe this is a memory, and some where there will be multipliers, because a microprocessor does a lot of things. And when it is built, fabricated, it's connected to the package using these connections here. So once it's built, it's a microprocessor, right? But we also have programmable or configurable integrated circuits. These are more homogeneous. This is the aspect from the outside when you take out the covering. And in the inside, these configurable devices, like the FPGAs, are simply an array of configurable blocks. So every block is not a particular device. It's something that can be configured to do some functionality. Okay, FPGAs are digital devices, so every block here can be configured to do some digital operation. And also these lines here goes in vertical direction and a horizontal direction are interconnection paths that can also be configured. So basically it's like a small electronics laboratory where instead of going to the shelf and taking the devices and connect them on a board, we configure the blocks with some functionality and then program the interconnections to interconnect those devices, and I have a circuit built that way. The good thing is that I can erase the configuration if I make some mistake, and I can reconfigure it with the correct design, or I can erase everything and use the FPGA chip for a different project and configure a new design there, and it can be done connecting the chip to the computer in just a few seconds. Okay. The problem with ASICs is that once the circuit is fabricated, it cannot be modified. If there's some mistake here, it cannot be repaired. Okay. There have been problems, famous problems with some processors that have some design flaws, and it was detected only after fabricating many million of devices. And the solution varies, but sometimes it can have to be done by software. So the once the integrated circuit technology arrived, there has been a huge improvement on the number of transistors we can put in a single chip, and it defines different generations of integrated circuits. Okay, goes from the small scale, medium scale, large scale, very large scale of integration, and ultra large scale of integration. This is the approximate dates when these were introduced and the approximate range of the number of transistors we can build inside. After the mid-80s, we stopped defining more generations, because actually from the 80s there's been a continuous increment in the integration density inside integrated circuits, so it's not very useful to define new generations. Basically, as technology improves, we can make devices smaller, and then we can put more devices. But as you can see, for example, the first integrated circuits only had a few transistors. They were used mostly for military and space applications. During the 70s, integrated circuits started to be used in consumer electronics and later in microprocessors, so it made it possible to build microcomputers that people could buy at the end of the 70s and at the beginning of the 80s. And during the 80s decade, we were able to put more than 1 million transistors in an integrated circuit. In this decade, it was important to develop design automation tools, computer programs that helped with the design and implementation of integrated circuits. So, because the complexity could not be handled by hand, the first integrated circuits were designed on paper, on big sheets of paper. But with complexity increasing, computers are used to design electronics. Electronics that build computers that will be used to design new electronics, and so on and so forth. So at the mid 80s, there started the concept of system on chip, because with more and several million transistors that we can put inside a single chip today, we can build a whole computer, for example, inside the single chip, not just the microprocessor, but everything else. In today's mobile phones, for example, we have the microprocessor. We normally have several cores, which means several microprocessors, but in the same chip we have the communications electronics, the encryption electronics, and everything else. It's a single chip for everything, which is the idea of the system on chip technology, or SoC. This, to have an idea of this evolution, before the 50s, when electronics were done with vacuum tube, before the invention of the transistor, a computer, one of the first computers like the ENIAC, will occupy a whole room. So the computer is the whole room. All these things around are the different devices and parts of the computer. Okay, people actually walked inside the computer. Okay, it consumes a lot of power. It was not a very fast computer with today's standards. With the invention of the transistor, which is much smaller, that's basically the same job, but it's much smaller, much faster, and also consumes far less power than the vacuum tubes. We could build more smaller computers, like this one from the mid 60s. Okay, so this is still big, but it was much more powerful, and it's just a big machine, not just a set of machines inside a room. With integrated circuits, we could do computers that was a million times smaller, that were a million times faster, consumes a million times less power. Okay, so today we have a microprocessor that basically does everything previous computers were able to do, and we have a computer as small as a laptop or as small as a mobile phone. This huge evolution of the electronic technology can be expressed, is typically expressed with the Moore's law. Gordon Moore was an engineer in Intel that at the beginning of the 70s, when the first microprocessor was designed and built by Intel, the Intel 4004, he anticipated that the density of transistors that the engineers were going to be able to put inside a single chip will approximately double every 2 years. Okay, and it's been like that for a very long time up to today. Today it's a bit more slower evolution, but it's been like that. This is a logarithmic scale. So if you can see, we started with the first microprocessor with a few thousand transistors, and now we have microprocessors that have more than 10,000 million transistors. Okay, this is still evolving. We design more and more complex chips, but now an important challenge is the power consumption. The chips consumes less power than before, but the problem is that this power is consumed in a very small area, so the power density is higher, and it makes temperatures to be very high inside the processors. Okay, that's why modern typical desktop computers have big fans to cool them down. Okay, but this just to have an idea on how it has evolved and how this transistor count is in parallel with this transistor count evolution goes the power of computers. For example, more transistors make it possible to make more operations. Smaller chips, it makes it possible to make them work faster. So the power of computers evolve in the same way. If we do the same job, do it faster, consuming less energy, so the same evolution has been the energy consumption or the energy reduction. So all that technology development that we have seen and we still see around us for the last few decades is basically due to the evolution of electronic technology. Okay, that's it. Thank you.